Welcome back to our series on multivariable calculus. In this episode, we're going to talk about divergence and curl, two vector functions that will help us to describe vector fields more completely. In addition, we'll look at applications of divergence and curl, which will allow us to extend Green's theorem to cover some more forms of line integrals. First, divergence and curl. Let's recall that the gradient function was really a vector of partials. So it was the first partial with respect to x, the first partial with respect to y, and the first partial with respect to z. And this, in fact, is really just a partial of derivatives. That is, it's a vector, and the vector has components which are itself partial derivatives, which means the del function doesn't really have any meaning on its own. It's only when it's applied to another function or vector that it has true meaning. Well, the first thing we did was we took del f, or the gradient of f, where f was some function that contained x, y, and z components, so that del f really created a vector, and it was d dx of f. So its x component was the x partial, df dy. So its y component was the y partial, and df dz. So the z component was the z partial, and this actually formed a vector, that is, del of a function, even though the function itself might not have been a vector function, the derivative of it, the partial derivative through the gradient, actually did form a new vector. Well, that means del itself can kind of be represented as a vector in its own right. And that means that we could apply the vector dot and cross product utilizing the del vector itself. Well, let's take a look at those, because those are the definitions of our two new terms. The first is del dotted with some vector function. So this vector function would represent a vector field. And if it's three-dimensional, we would get del dotted with f. And keep in mind that del is the partial with respect to x, y, and z separately. And of course, the function f is going to have its own x, y, and z components, each of which could be multivariable functions. So del dot f would be partial with respect to x, partial with respect to y, and partial with respect to z. That vector dotted with a second vector that has f, which could be multivariable in x, y, and z, g, which could be multivariable x, y, and z, and h, which could also be multivariable in x, y, and z. But the dot product limits where these partials will apply. The partial with respect to x will only apply to f. The partial with respect to y will only apply to g. And the partial with respect to z will only apply to h. In addition, because this is a dot product, I will sum the results of these three partials, and it will form a new function or a scalar if we evaluate it at a point. This then is referred to as the divergence. The divergence of a vector field refers to how successfully that vector field flees from or heads towards a given point. So if I calculate del dot f and then I substitute in a particular point, I will get positive values that will grow larger and larger for this scalar function if in fact the vector field flees from that point and points outward. I will get negative values of increasing magnitude if that vector field points towards that point. And if the vector field points tangential to any line radiating from the point, I'll get a 0 for the divergence. Divergence is an excellent measure of how congestive a field is, whether that vector field points towards or away from a given point within the field. So that's the scalar product of the gradient vector together with some vector field, and it refers to the divergence of the field. Well, let's take a look at the second half of this coin, and that, of course, would be del crossed with F. Well, this one's going to be a little bit more difficult to evaluate simply because it's a cross product. And of course, to evaluate the cross product of two vectors, if it's three-dimensional, we're going to need a 3x3 matrix. The top line will be I, negative j, and k. And of course, these refer to the unit vectors in the three principal axes. The middle line is going to be the first vector in the cross product, and that, of course, is the partial derivatives. Partial with respect to x, partial with respect to y, and partial with respect to z. And of course, the bottom line are the three components of the vector f, f, g, and h. And you can see as a result of calculating this cross product between these vectors, we will get the following sets of terms. When I block out the I row and column, I'm going to get partial y of h, hy, minus the partial z of g, gz, and those will be in the I hat direction. Minus, because we get an extra minus for the j hat. Block out the j hat row and column, and I'll get partial h with respect to x, minus the partial of f with respect to z. And that will be in the j hat direction. Finally, plus the third term will block out the k row and column, and we'll get partial g with respect to x, minus the partial of f with respect to y. And that will be in the k hat direction. You'll notice that in this case, we get a vector as a result. This vector is referred to as the curl. And what the curl really refers to is the vector around which the vector field seems to be swirling in the right-handed direction, which means if you take your right hand and point your thumb along the direction of this vector, this is the degree to which the vector field will swirl around that direction. So, if the curl has a clearly defined vector with a large magnitude, that means the field is going to curl in that direction around that vector more successfully. If instead we had a field with a large divergence, that means it's going to move inward or outward towards a point, and it won't really curl very much. And of course, this vector will either be equal to the zero vector, or it will be a very small magnitude vector. So curl refers to how much a field swirls, and divergence refers to how much a field moves in and out. Now, in and of themselves, these have some really interesting applications, particularly for field theory, electricity and magnetism, and Maxwell's equations. But for our purposes today, they're really just going to form components of extensions of Green's theorem that is basically going to allow us to further evaluate line integrals that fall into categories that these can help with. So let's take a look at those. The first category we're going to look at, and again, these two theorems I'm going to write are just both extensions of Green's theorem. The first one deals with a double integral, again, over some sort of area within the xy plane. And within it, what we want to do is take the double integral of the cross product, that is the curl of del curled with f. And then we're going to dot that with the k hat vector, dA. If we're going to evaluate that cross product and dot it with the k hat vector, that is then equal to, through Green's theorem, the single closed loop integral over a curved path around this boundary of instead the f vector itself dotted with dr. That means if we want to evaluate f dot dr, we can also evaluate it as a two-dimensional integral by taking its cross product with f, that is evaluating the curl, dotting it with k. In essence, what this evaluates, that is a way to describe this, is the degree to which the vector field agrees with the outer boundary of an area. In essence, it's like calculating the curl for the edge. And what this says is that will equal the sum of all the individual curls across the area summed together. So we can either evaluate many small curls over the area, or we can just evaluate the curl at the extreme and look at how the function itself matches to the outer boundary. And Green's theorem says these will both evaluate to provide you with the same answer. So once again, just like with Green's theorem, this gives you a choice. If you're asked to evaluate this integral, you can then instead evaluate this one. And if you're asked to evaluate this integral, then of course you can instead evaluate this one. Okay, the second one involves an application of divergence. Suppose you need to evaluate the double integral of del dotted with f dA. Well, then once again, according to Green's theorem, what you can do instead is do the closed loop integral around the boundary here of f dotted with the normal vector ds. So once again, we can turn a two-dimensional integral of a dot product into a one-dimensional integral of a dot product between the vector field f, and this would be the normal vector on the surface. An interpretation of this one is as follows. This will integrate, in essence, how successfully f and its first derivative basically flee the center. We're evaluating the divergence as a function of the area. So over the entire area of the region, we're looking at how successfully the vector field points outward. What this is doing, NDS is actually tangent to the edge. So it runs along the edge and then it measures the dot product between the vector field and the tangent line to the edge. And of course, what we're looking at is how successfully the vector broaches the boundary of the edge, because NDS runs perpendicular and we're looking at the dot product. So it's how successfully the vector field matches outward moving vectors along the edge. In essence, this says we can measure the vector field success at the edge, or we can measure the vector field's divergence everywhere throughout the area. And just like Green's theorem, these allow us to take divergence and curl and evaluate them on the boundary as opposed to evaluating them throughout the area. View these as extensions of Green's theorem. And for most of these problems, we're not really provided with the specific integral. We're asked to perform one or the other of these, and then it's up to us to decide, do I want to evaluate these integrals along the boundary, or do I want to provide an area integration over two dimensions? And in every case, it really depends on the limits of integration as to whether a function describing the boundary is better than integrating over an area. And you'll see that different problems will provide you with different indications for how to evaluate these integrals. So divergence and curl, which you will see over and over again in other applications, this is their definition. And for our purposes, we're using them to extend Green's theorem as additional ways to evaluate the integral of f dot dr, the humble line integral which we have been working with for many days now. And now we have the opportunity to incorporate divergence and curl as a way of integrating this line integral.